So ethers are actually very good solvents for a lot of chemical reactions because they're fairly inert. They don't react with a lot of things, but they will react with strong acids. So if I have this ether and I treat it with HBr, or I could use HI, we have to think again about the mechanism. Who has electrons and who wants them? Well, certainly the H plus is who wants them. So then I have to look at my ether and figure out who has them, and who has them is oxygen. So oxygen comes over and gets protonated, is the first step. And then the second step is bromide is going to come in and attack. Now it can actually come into either side, so you can draw it either way. So I'll draw it one way first. So here I'll have it add to the methyl group. This bond breaks, goes on oxygen, and I have this alcohol plus CH3Br. Now I can have it go on the opposite side. Now I can have it add to the opposite side as well. In that case, I've got an alcohol with only one carbon, so I've got methanol plus ethyl bromide. Now eventually, once it adds, it can keep adding as well until I have both sides brominated. So if I have more HBr in solution, my alcohol can get protonated, which then can react with another Br minus. And you lose water. And that's just the first reaction that we learned with turning an alcohol into an alkyl halide. So in the end, what you end up getting from this reaction is both sides of the ether with excess HBr, both sides of the ether become brominated. So how are epoxides going to react? So the first thing you have to ask about is, do they have a good leaving group? And if I bring in a nucleophile and attack one end of my epoxide, my leaving group is an O minus. So it's not really a good leaving group. However, we can still make this reaction happen, and the reason that this reaction will still happen is because there's so much ring strain here. Where here, there is no ring strain, or angle strain. So what we have is we have a strained ring that has two polar bonds between carbon and oxygen that have partial positives at the carbon, so that a nucleophile can come in and attack. So let's take a look at a mechanism. So if I have an epoxide, I react it first with cyanide, and secondly with water. So it's back to the same question as before. Who has electrons? So the cyanide has electrons, and who wants them? One of the carbons that are bonded to oxygen have the delta pluses, so that's who wants them. So if I have this cyanide come in here, remember, SN2 substitutions like this have to happen through backside attack. So that cyanide has to come in opposite the leaving group. So my cyanide has to be coming from behind. This bond here to oxygen is still intact, so that one is still coming out in front of the plane, O minus, then just get reprotonated by water. Now we can do this exact same reaction with acidic conditions, which just changes the order of the reaction a little bit. The results are similar. So if I react this with HCl, now the first thing that's going to happen is my oxygen gets protonated. Who has electrons and who wants them? The hydrogen really wants somewhere to go. The oxygen has electrons. And now what I have left in solution is a chloride. And so now the chloride comes in through backside attack, displacing this bond to oxygen. And my result, I have a chloride going back and an OH coming out. So you notice anytime you're going to ring open an epoxide, you always get anti-stereochemistry, which means that the two groups, one is forward, one is back. That's as opposed to the opposite if we had both of them going on one side. This would be syn stereochemistry. Syn means that two stereocenters next to each other are on the same side of the molecule. Anti-stereochemistry means that two stereocenters are on opposite sides of the molecule. Now we can also do this kind of a ring opening with acid and water. So if I have a whole bunch of water around and a little bit of acid, maybe like sulfuric acid, which doesn't have a good nucleophile once it gets protonated, like the chloride from HCl. So if we do this, the first step is still the same. Protonate my epoxide. And the next step is water is my nucleophile. So who has electrons, who wants them? The oxygen from water has electrons. The carbons here want them, pushing off one of the bonds to the epoxide. Remember, it had to come from backside attack. So again, I have anti-stereochemistry. And now my molecule is still protonated, so I have to have something else come by and deprotonate. So I would just use another molecule of water to come by and take off one of these protons to make my molecule neutral.